Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of organic chemistry lectures and solutions to homework problems. In this Scribblecast lecture, we are pressing on with our examination of alkyl halides. We have established already that alkyl halides can react via two types of reactions. One called substitution. In fact, it's called nucleophilic substitution because the attacking group adds as a nucleophile. It reacts as if it's being attracted to a carbon that has a positive charge. Objects that attack carbon that are positively charged are referred to as nucleophiles. The same attacking group, say hydroxide, which is called a nucleophile when it attacks carbon, if it attacks a proton, as it does in elimination reactions, is referred to as a base. And so we have these two terms, nucleophile and base. And what we want to do is be able to contrast base strength with nucleophile strength. After all, if something that is a strong base but a weak nucleophile, it might prefer elimination reactions. Whereas if something's a strong nucleophile but weak base, it might prefer substitution reactions. Hence, we need to have a good understanding of nucleophilicity versus basicity. Now, basicity, we understand how it is measured. We can use pH to determine base strength. We can determine an equilibrium constant for a acid-base reaction, and we've done this in past lectures and examined this. These equilibriums are measured in Ka values, and these can be converted to a negative log called pKa's. Now, given a pKa value, one can determine whether something's a strong acid or not. If something's a strong acid, it's a weak base, and vice versa. So basicity is readily determined using pKa values. But how would one determine nucleophile strength? Well, in a substitution reaction, as we've already written, we can use methyl X. Attack it with some nucleophile, say a negatively charged nucleophile. And when we mix the two, the nucleophile attacks a positively charged carbon, the delta plus on the carbon. It's not a full positive charge, just a small partial positive charge. And the electrons on the X actually move out towards the X. And you get substitution. The nucleophile is now bound to the carbon, and the X leaves, taking all electrons, so the carbon X bond breaks homolytically. Both electrons go to the X, and it leaves with a negative charge. Now, if we want to understand nucleophilic strength, we have to keep every variable constant except the nucleophile. That is, we must use the same solvent, same temperatures, same reaction conditions. In fact, we must use one type of methyl halide. A common one is to use methyl bromide. So I take methyl bromide in a specific solvent system and I start testing it with different nucleophiles. And what I can do is time the reaction, determine how long it takes to produce the nucleophile attached to the CH3. This timing of the reaction is termed as measuring the rate of reaction. Nucleophiles that react faster are stronger nucleophiles. Nucleophiles that react slower are weaker. So what factors favor nucleophilicity? What factors favor nucleophilicity? Well, if I look at for specific factors that favor nucleophilicity, the first thing that is obvious, if I even look at the nucleophile in the above reaction, is that if carbon has a delta plus, a negative charge will help attract the nucleophile towards that positive. Hence, negative charges help favor nucleophilicity. And so nucleophiles with a negative charge will be more nucleophilic than identical groups or similar groups without the negative charge. And we can draw some examples of that. Hence, if I take H2N, which has two lone pairs, and give it a negative charge, okay, H2N, let's fix that. That's a lone pair, that's a negative charge. It is a stronger nucleophile than NH3, which is neutral. Notice this comparison only works if you're comparing like groups. HO minus is a stronger nucleophile than H2O. Let's pick an organic molecule, such as carboxylic acid. So the deprotonated carboxylic acid, the CO2 minus, negative charge here, is a stronger nucleophile than the exact same carboxylic acid where it has not lost its proton. So negative charge favors nucleophilicity. How about basicity? We already know our trends for acidity in periodic table. In a general period in the periodic table, as you go to the right, electronegativity increases. Because electronegativity increases, the atoms increase in their ability to give up a proton, because when you give up a proton, you gain a negative charge. So fluorine is more electronegative than oxygen, so HF's a stronger acid. Well, that means F minus is a weaker base than hydroxide. And we can follow this trend in terms of base strength. If I pull a proton off methane, I'll get CH3 minus, where there's a lone pair. Well, carbon's not electronegative at all. It doesn't want that negative charge. This guy's going to want his proton back, which means CH4 is a very weak acid, but when it's lost its proton, CH3 minus becomes a super powerful base. CH3 minus is a stronger base than the corresponding NH2, which has two lone pairs, minus. So NH2 minus is a weaker base, if you like. Let's move this negative over here. NH2 minus is a weaker base than CH3 minus. NH2 minus is a stronger base, of course, than hydroxide minus. Hydroxide minus has three lone pairs. And a hydroxide minus is a stronger nucleophile than F minus. Oh, sorry, stronger base. That's the nucleophile? I meant base. So in terms of base strength, we've already established our periodic table trend for a row or period. Stronger acids are to the right, weaker bases are to the right. If you're stronger acid, HF's the stronger acid, F minus must be the weakest base. So in terms of base strength, CH3 minus is stronger than NH2 minus, who's stronger than OH minus, who's stronger than F minus. Well, it turns out, in general, stronger bases are better nucleophiles. This works for the period or row in a nucleophile, in a periodic table. So this works for rows in the periodic table. So if you take a row in a periodic table, the stronger base is to the left, the stronger nucleophile is also to the left. So in this case, hydroxide is both a stronger base and stronger nucleophile than F minus. Likewise, NH2 minus. Okay. What about groups? That's only one half of the periodic table. What about the groups? Well, we know the trend in acidity. HF is a weaker acid than HBr, which is a weaker acid, HCl, sorry, which is a weaker acid than HBr, which is a weaker acid than HI. Remember, this is caused by poor orbital overlap. I is a very large atom. H is really, really small. If I take a large I and I overlap it with a tiny hydrogen, I get a small percentage of orbital overlap. Very tiny orbital overlap. And because of this tiny orbital overlap, the bond is weak, it breaks more easily. Well, that means HI is the strongest acid. That means I minus is the weaker base. So in terms of base, if this is acid strength, this trend, HF is less than HCl, then F minus is greater than, in base strength, Cl minus, who's greater than Br minus, who's greater than I minus. And that's base strength. So the weakest base is I minus. If you're the strongest acid, you're the weakest base. You want to give up the proton, you can't want to keep it. Well, does this trend hold true for carbon? Well, here's the problem. Carbon is much bigger than a hydrogen. The carbon atom, because it's much bigger, will give you more orbital overlap. So the poor orbital overlap becomes less of an issue. Okay? I mean, it's still there, but it's not as exaggerated as in the case of a hydrogen. Furthermore, if I have a carbon that has a delta plus on it over here, and a big iodine, iodine is more polarizable. What does that mean? Because the iodine is more polarizable, it's bigger. Polarizability is a measure of an electron's ability, or an atom's ability to respond to a changing electric field. The changing electric field is approaching the delta plus on carbon. Because he's bigger, he can move electrons a further distance within its orbitals. And the net result is an easier movement of electron density towards the carbon atom. So, because it's bigger, because it's more polarizable, I is a stronger nucleophile. That means the trend does not parallel basicity. The weakest base is the strongest nucleophile in this case. Okay, so if I rub this out, if that's the base strength trend that we've got drawn there, where I is actually less than Br, Br is greater than I can reverse that trend for nucleophile strength. F minus is less than Cl minus, who's less than Br minus, who's less than I minus being the strongest nucleophile. All right? So in terms of nucleophile strength, basicity and nucleophilicity do not parallel down a group. The strongest nucleophiles are to the bottom, but they are also the weakest bases. Now that's really surprising, especially for the iodine case, because if you remember last lecture, who was the best leaving group? The best leaving group was I minus because it's a weak base. It's the weakest base. Isn't that an interesting paradox? The strongest nucleophile in this group is also the weakest base. The strongest attacking group is the best leaving group. Seems like a contradiction, but in actual fact, it holds true. Okay, let's look at some groups. As I said, or some examples of this as we look down groups of stronger nucleophiles, some trends. As I said, the more polarizable, the more distorted the electrons are, the better they are able to donate. The more electron pairs, more available for bonding when the orbitals are larger. One point to note is solvation does play a major role in this. Water dipoles are held more tightly to the smaller halide ions that have higher charge size ratios. So nucleophiles in solvents that are larger can move through the solvent more easily and attack the carbon as well. Some trends. Well, if, for example, I take a molecule like dimethyl sulfide that has sulfur in it, dimethyl sulfide is going to be a stronger nucleophile than methanol. Which has oxygen. Or a stronger nucleophile than dimethyl ether, which also has oxygen. Dimethyl ether, of course, is a gas, so it would be harder to use it as a nucleophile, but you could. HS minus is a stronger nucleophile, has 3 lone pairs on it, a stronger nucleophile than HO minus. Okay, this would have 2 lone pairs. Might as well show the lone pairs on these. Cl minus, as you go down the group, we've already established this one is a stronger nucleophile than F minus. Again, there are lone pairs around these. Both Cl and fluorine have 4 lone pairs, 8 electrons. Triethylphosphine. Three ethyl groups attached to a phosphorus, which will have 1 lone pair, is a stronger nucleophile than triethylamine. And thiophenol, benzene, with a sulfur off of it. A thiophenol anion, thiophenolate, is a stronger nucleophile than the phenolate anion or phenoxide. And all these hold true because sulfur is lower in the group than oxygen, phosphorus is lower down the group than nitrogen, and chlorine is lower down the group than fluorine. Okay. The last point you want to make, or we want to look at, is that for a series of compounds in which the same atom is the nucleophile, nucleophilicity parallels basicity. In essence, we've already done this in the first point when we said negative charges are more nucleophilic than neutrals. And I'm going to just pick some. Let's look at the acid and its conjugate base. And I'll just pick a few. When you compare something like ethanol, to its deprotonated form, which would be called ethoxide. Lose a proton in ethanol, and you haven't learned this yet, but it's called ethoxide. It would have 3 lone pairs. This guy only has 2 lone pairs. Well, the negatively charged ethoxide is the stronger nucleophile because you're attracted to a positive. If we're comparing phenol to phenoxide, where it's lost its proton, two lone pairs on the oxygen. The phenoxide is the stronger base. And even when you take this to positively charged species, like H3O+, you can compare it to neutral H2O. Well, even neutral H2O is closer to being negative than a positively charged species. Case of H3O+, it's the weaker nucleophile. Now, if I was looking at acid strength, I'll call it acid strength. I'll just put STR. This is the weakest acid up here. So ethanol is your weakest acid. And we're getting stronger in this way. Notice the strongest acid is the weakest base. So if we're doing base strength, STR period, then H2O is the weaker base. And the stronger bases are up. They're opposite. Now these lines are referring to the acid strength and the base strength here. But when comparing nucleophile strength, the strongest nucleophile is the conjugate base. Now this holds true also for, if I repeat this trend, for amines. NH2- is the stronger nucleophile. NH3 is a stronger nucleophile than NH4+. And if we want to do aniline, the protonated version of aniline is a weaker nucleophile than aniline itself. Now, one point we should make, and we've already mentioned this, and again, you could do the same thing. If this is my acid column, this is the weakest. NH3 is the weakest acid, whereas the anilinium ion would be the stronger acid. And the strongest acid's base is reversed. That would be the weakest base, and the strongest base would be up here. So if you're looking down these, they're also written in strongest base is going up on this side. This is acid strength for these. This is base strength. Now, again, the right-hand column is the strongest nucleophile, but a couple points about this group and this group. Note that they have no lone pairs. They're not only weak nucleophiles, they're terrible nucleophiles. They can't be nucleophiles. You need at least one lone pair to act as a nucleophile. All right, so there are some trends in nucleophile strength based on conjugate acids, conjugate bases, and trends in the periodic table. But what if there's no simple trend? What do you do when the exact simple trend isn't available to you. You're comparing elements way off in the periodic table. You may be comparing HS minus to I minus, or I minus to CN minus. Molecules that have no groups, that have no simple relationship. Well, in that case, you just have to memorize a trend of nucleophilic strength. So I'm going to give you now a nucleophilic strength trend that you really need to memorize. Nucleophilic strength. And this nucleophilic strength trend, what we have here is we're going to start with the strongest nucleophile being HS minus. And HS minus would have 3 lone pairs. RS minus would be next. R symbolizing any alkyl group, methyl, ethyl, propyl, isobutyl. And these two are very close in value. Following that is CN minus. CN minus is C triple bond N. And there's a lone pair off of both atoms. CN minus, okay, sometimes just written CN minus. Okay, that's a stronger nucleophile than I minus. I minus is a stronger nucleophile than alkyl oxide, RO, 3 lone pairs, minus. RO minus, the R group again is some alkyl group, methyl, ethyl, propyl. That's stronger as a nucleophile than NH3. And NH3 is stronger as a nucleophile than hydroxide with 3 lone pairs. Now, this is interesting. Let's compare NH3 and OH for a second. You know, I told you that you have to, when you look at the negative charge concept, you have to compare the same group. Like, if you want to find out who's stronger negatively charged, you compare hydroxide to water. And you say hydroxide has the negative charge, it's a stronger nucleophile. Notice that you can't compare it to anything. I mean, if you just went by negative charge and neutrality, you would have said hydroxide stronger nucleophile than ammonia, NH3, which clearly is incorrect. So when you use the negative charge rule, you only can use it when comparing to similar groups, identical groups. NH3 is a stronger nucleophile because while hydroxide has the negative charge, oxygen is more electronegative than nitrogen and able to stabilize that negative charge. And so ammonia donates better than hydroxide as a nucleophile. After hydroxide comes a N3 minus molecule, which has a lot of resonance structures you can draw. I'll draw one of them. If you draw this structure, N3 minus, and you get 2 electrons there, you get several lone pairs on the ends. The negative, if you do the formal charge, you get a minus, plus, minus to this molecule. So that's what the molecule looks like, for those who are curious. N3 minus is a weaker nucleophile than hydroxyl. And then comes Br minus. After Br minus comes CH3, CO2 minus. Remember, let's rub this out. Br minus has 4 lone pairs around it. I can draw those lone pairs for you. So you have 1, 2, 3, 4 lone pairs. CH3CO2 minus is a carboxylic acid where the double bonded, let's put it down. The double bonded oxygen has 2 lone pairs and the single bonded oxygen has 3 lone pairs. So it's a carboxylic acid that's lost its proton. CH3 minus is stronger nucleophile than Cl minus. And that's a stronger nucleophile than F minus, which is a stronger nucleophile than H2O. And I'm going to just put up here, grouped with H2O, also the alcohols, ROH. So the alcohols up here as well. These are R, could be a methyl, which would be methanol, and ethyl, ethanol, isobutyl alcohol, any alkyl group. And I'll rub that off. So this is the trend you need to memorize that's very useful. Now, during our discussions of alkyl halide reactions, I will often be using the term strong nucleophile, weak nucleophile. And this term, you have to understand, varies a little bit. I, for example, might say hydroxide is a weak nucleophile, but I might be talking relative to I minus, and a hydroxide is weaker than I minus. And then the very next lecture I might be saying hydroxide is a strong nucleophile because I'm talking about it compared to chloride. It would be handy, just for simplicity's sake, if I would give you a rough mark on here of where I usually draw the demarcation between strong nucleophile and weak nucleophile. And if I was to do that line, I would put it here. Everything on this side, I will be using generally, not always, but generally the term weak nucleophile. Now, I could call CH3CO2 minus a strong nucleophile if I'm comparing it to chloride or fluoride. But generally speaking, when I'm saying, oh, weak nucleophiles, I'm referring to these guys right here. Everything to the left, including the first row, will be called the strong nucleophiles. Okay. Now, one more important factor that affects nucleophilic strength, when you're comparing identical nucleophiles, or similar structure nucleophile, and that is steric hindrance. Steric hindrance. Steric hindrance refers to the steric bulk around the attacking nucleophile, the atom that's acting as a nucleophile. It talks about the bulkiness of the groups. For example, suppose I have ethylamine and I compare it to diethylamine. Well, it turns out that ethylamine is a stronger nucleophile than diethylamine. Why? Well, remember, the nucleophile must attack a carbon that has a halide on it. And off of the carbon, there is usually other groups. Now, sometimes these groups are just hydrogens. But sometimes they're carbon, and they have groups off of them. And so to get in at this carbon, the more groups off of the nucleophile, the more sterically hindered it is, the more bulk there is, the more these groups interact, and the more it is harder to attack that carbon. Because two ethyl groups create more bulk around the nitrogen, it is harder for the nitrogen to get at the carbon. And hence, if it's harder to attack the carbon, it takes longer, that means it's a weaker nucleophile. So, for example, triethylamine 3 ethyl groups would be even worse. Well, does that parallel basicity for this? Well, remember, basicity is different. Basicity, the thing that has to get at the nitrogen, is a proton. And a proton is really tiny. There's no electrons around it. A tiny proton can go in here really easily. So in fact, the strongest base is the triethylamine. So this steric hindrance effect does not affect basicity. However, nucleophilicity, the less bulk, the stronger the nucleophile. Let's look at another example in which this holds true. Create some room here. And that is when you have an alkoxide. An alkoxide, like ethoxide, is a stronger nucleophile than when you start putting more methyls on the first carbon. Because these extra methyls can block the high oxygen and make it harder to attack that back part of the carbon. And so, the worst case scenario being this molecule, tert-butyl alcohol that loses its proton, is called a tert-butoxide. We'll be learning that name later on. So again, steric bulk can cause steric hindrance. The bulkier the organic material around the nucleophile, the nucleophilic atom, the harder it is for it to attack the carbon with the plus. Note again, this does not affect basicity. Now, one other thing can affect the speed with which the nucleophile attacks, and that's why when we did these nucleophilic strength measurements, I said you had to keep the solvent the same. The type of solvent you use can influence strongly the speed with which the nucleophile attacks. Protic versus aprotic solvents. Protic solvents comes from the word proton and refers to the ability to hydrogen bond. Protic versus aprotic solvents. Solvents that can hydrogen bond are Protic. Let's look at some examples of each. Protic solvents would be solvents like water, methanol, ethanol, so any ROH alcohol. These are examples of polyprotic solvents. Examples of aprotic solvents are dimethyl formamide, alias DMF. Dimethylformamide has this structure. Two CH3s off of the nitrogen. Dimethyl sulfoxide. called DMSO for short. Dimethyl sulfoxide looks like this. And that's an H. Dimethyl, let's make a little more room. Dimethyl acetamide. Dimethyl acetamide. It's just like dimethylformamide. Instead of the H off the C double bond O, there's a CH3. And two CH3s off the nitrogen. And lastly, of course, acetone. Oh, by the way, that's DMA for short form. Acetone. All of these solvents, acetone structure, you know, had it and used it in the lab quite a bit. All of these solvents, all of them, are incapable of hydrogen bonding. Now, how is that a problem? How would that affect the rate with which the nucleophile attacks? Well, let's consider the protics. Because polar protic solvents have hydrogen bonding, they have a delta plus on H. The delta plus on the H can solvate the nucleophile. Let's say my nucleophile is a halide. This guy is searching for an organic molecule to attack. Water has a delta plus on its H. And delta pluses are attracted to X minus. So there's a hydrogen bond. That means this solvent bonds really strongly to X minus. Polar protic solvents can solvate strongly through hydrogen bonding anions. That means the anion must break through the intermolecular force of attraction before it can attack. Before it can attack the organic substrate. Now, hydrogen bonding is one of the strongest intermolecular forces. It is enough to slow down the attack. So if you want to slow down your nucleophile's attack, you use a polar protic solvent. Aprotic solvents can solvate cations because they have these electronegative groups with delta minus, but the dipole is much weaker than what we get in hydrogen bonding. So then they don't solvate well anions. And so if you use a aprotic solvent, the anion can move in on the organic substrate much faster. And so polar protic versus aprotic solvents, that is solvents that have hydrogen bonding versus solvents that don't, as an intermolecular force, can be used to control the rate at which the anion attacks. It can slow it down a bit. Now, sometimes this effect is not significant on rate, and sometimes it's hugely significant in certain mechanisms. Sometimes it's a small effect, sometimes it's a large effect. And we'll be seeing that when we actually look at the reaction mechanisms themselves. Now, this brings us to a point we're almost ready to begin looking at the reaction mechanism. The reaction mechanism. Now, a reaction mechanism is more than just drawing out the simple reaction. In a reaction mechanism, we draw out more than the simple reaction. We actually look at the events that take place at the molecular level, all of the events that take place at the molecular level. A reaction mechanism is a detailed description. A detailed description of all structural and energy changes that occur as reactants are converted to products. All of the structural and energy changes as you form products. It tells you the process of the reaction. It gives you the process of the reaction. For example, which bonds are broken? It tells you what order they're broken in. So in what order? In what order are they broken? Tells you the number of steps. In the reaction. It tells you the speed or relative rate. Which step is faster? Which one's slower? The relative rate of each step. It includes a mechanism includes all of the electron movement. And what does electron movement do? That's the making and breaking of bonds. It describes all bond formation and all bond breakage. It includes a description of the spatial relation of atoms. The spatial relation of atoms. Chirality, the role and effect on chirality. The structural and energy changes at all stages. So, process of reaction, which bonds are broken. It gives you the mechanism includes, what the mechanism includes, and it must explain. It should explain any changes in stereochemistry, or why the stereochemistry does not change. So it must explain the stereochemistry of the reaction. Does R become S, or does R stay at S? The geometry of the attack. Also structure, which is stereochemistry. And hybridization changes. Geometry and hybridization of the products must be described in detail. It must explain all, not just one or two, it must explain all experimental observations. Now, we've already had our first mechanism, and that was in the chirality section, the inversion of amines. In the inversion of amines, we came up with an explanation of why amines that are chiral, when placed in pure enantiomeric form in a bottle on a shelf, will in a short time form a racemic mixture. And we explained this by describing how it inverted through an sp squared hybridization. In essence, this was a first, not reaction mechanism, but mechanism of change of chirality. Now, you must remember that a mechanism is a theory. It's a proposal. It is a proposal that helps interpret experimental observation and can never, ever be proven. Science does not reveal truth. Science reveals plausible explanations of observable experimental phenomenon. And the theory only stands as long as it is supported by experiment. And theories may stand for a period of time, but eventually be proven wrong. So, while theories can never be proven correct, they can be shown to be incorrect, eventually. It's very subjective what mechanism is chosen. The most reasonable mechanism which is consistent with the experimental data is chosen, and often we rely on previous precedent mechanisms that work with previous similar reactions. And if it can explain all the experimental observations of the present reaction, that mechanism is often used. What steps should be used? When determining a reaction mechanism, what do you have to do? Steps used to determine your reaction mechanism. Well, I'm going to list them and then just talk about them. You will have to take notes down on this. First off, you need to identify all of the products. Because organic reactions often can follow more than one mechanism, producing many products, every product must be identified. That is crucial. 2. Intermediates. does the reaction produce any intermediates, species or compounds that form during the reaction but then disappear as they go on to react? Does the reaction go by a one-step concerted process, no intermediates forming, or the series of multiple steps that allow intermediates to form, hang around for a while, and then go on and react? We must know the stereochemistry in the reaction. Stereochemistry is very important. If you start out with a chiral center, a pure enantiomer, does the chirality stay the same? Does the three-dimensional structure of the molecule remain unchanged? Or does it change its handedness and form a new structure of the opposite chirality? Or do you lose your chirality and end up producing a racemic mixture? This is very important. Kinetics. Kinetics is determining the rate of reaction. And not only do you have to determine the rate of the overall reaction, you need the rate of each step in the reaction. If there's a single step, what is the rate of the reaction? Upon what does that reaction depend? Is it unimolecular, bimolecular? If I change the concentration of the reactants, does the reaction speed up? Or is there no change? All of the factors that affect the rate of reaction must be investigated. Does solvent affect the rate of reaction? The factors that affect kinetics are crucial to understanding what is occurring in the reaction mechanism. Is there a catalyst? Does your reaction proceed through some catalytic process? Remember, a catalyst is something that causes a reaction to occur, but it itself is unchanged by the reaction. So, catalysis, catalytic reactions, let's call it, let's go catalysis. That might be better. Catalysis, check for catalysis, and also check for any solvent effects. And this solvent effect, as I stated, can influence your rate of reaction as well. Catalysis and solvent effects. Are there substituent effects? Does the rate of reaction, does the behavior of the reaction, substituent effects? You must explain what happens when you go from methyl bromide to, say, butyl bromide. If we put more bulk, more substituents off of the alkyl halide, how is the reaction mechanism affected? Some mechanisms involve abstraction of hydrogen. In such a case, such as the elimination reaction mechanism we covered last lecture, one could ask, does changing hydrogen to deuterium affect anything? And so, use of isotopically labeled compounds can be important in determining if there are any isotopic effects. Often this is used in the case of hydrogen, where you replace it with deuterium. Do isotopically labeled reactants affect the outcome of the reaction? Sometimes, using isotopes, one can tell or help determine which mechanism is wrong. You might have two possible reaction mechanisms, and it isn't until you use an isotope that you can actually determine which one doesn't support the experimental evidence. Note again, you can never prove one right. It may be the one that still supports everything is also wrong. You just don't know it. But sometimes isotopically labeled compounds can be used to help distinguish between two mechanisms that both look correct. Reaction mechanisms. They are important. They can aid in the classification and understanding of a vast array of reactions. They generate a pattern out of what would have been just a large number of unrelated reactions. They allow us to make sense of a huge volume of material and can be used to predict outcomes of reactions and very often improve the yields of reactions. Well, we finally arrived. In the next Scribblecast lecture, we're going to be looking at our first full-blown reaction mechanism. I hope this has been useful. My name's Dr. Brian Lloyd. This is my Scribblecast lecture.